Good morning. So, first of all, thank you guys for coming. I was here a few minutes ago and there were not so many people, so I'm happy to see there's a few. I just checked. My name is Amos Breifogel. So I work for a company called Stratasys. Who here has ever heard of Stratasys? Oh, also, this is going to be an interactive presentation, so get ready. So good. A few people have heard of Stratasys. Does anybody use 3D printing in their companies? Does anybody use additive manufacturing? Is anybody really confused about why there's two terms for that? Okay, good. So I don't have to explain that. So what I'm going to talk about today are a few of the different applications of additive manufacturing. So the reason we call it that is that there's this 3D printing world that came from prototyping. So it was 30 years ago, the first 3D printing companies came to be to build prototypes, to help with development work, help you move faster. As the technology evolved, we got better materials, we got better machines, better repeatability, and now we can actually move into manufacturing, whether we're doing tooling, production parts, or anything else around the manufacturing environments. So today we're going to talk about a few topics. We're going to look at what we can do with composite layup tooling. We're going to look at some ways to do sacrificial cores. We're going to look at some of the trim guides around those and some other tooling for composites you can use. Then finally, we'll look at how we can actually do direct production of parts. Any questions before we get started? Okay, good. So the first thing we look at, if you haven't seen a 3D printer before, this is what one looks like while it's running. So this is one of our larger machines printing with a material called Ultem 1010, which is a PEI. So the cool thing about this material is that it can withstand a high enough temperature that you can actually do composite layup tooling off of it. So this example is from Team Penske in the US. So this is a racing team that races in several different series. And what they're actually doing is they print a tool and they can lay up composite parts directly on that. So it can go to 180C and they can produce two parts over and over. For them, they only need a few of each part, whether it's 1, 5, 10, 50. It's not a problem for this type of tooling. So for them, it means that we can go from creating tools in weeks to hours or days. So if we look at this example from Dassault Falcon Jet in the US, their traditional tool is shown in the top left here. So this tool weighs 75 kilos. So who here actually processes composite layup parts? A few people? You know what an autoclave is? I hope. If not, just look around. Someone will definitely explain it. So one challenge with this, when you have tools that are really heavy, is that they do the layup on the tools, and then you still have to get that into and out of the autoclave. So one big advantage with 3D printing is that this tool weighs 8 kilos. So from 75 to 8. That means that you don't need a fork truck to move this around anymore. One person can pick this up and actually just move it. So the lead times on these, to make the tool in the top left here, we're looking at something like 14 weeks. To make the tool on the bottom is around 1 week. So this includes building the tool, finishing the tool, and doing anything else you need to do to get it ready to produce parts. So you can greatly reduce the lead time that people have. So if we look at different industries, the racing industry, so this is from aerospace, but the racing industry, lead time is the most important thing they have. So if you can go from having a 2-week lead time to a 1-week lead time, it means they win more races and they should use the technology more. So for aerospace, it's also a big cost for development. So the faster you can do things, the less time you're waiting on POs and the less time you have to wait for all the other items that are attached to this. Just out of curiosity, do we have anybody here from the racing industry? Anybody here from aerospace? Automotive? So do the rest of you just not have jobs, or? No? Okay, we'll talk later about that. If you need jobs, let us know. We're always hiring. So moving on from the composite layup tooling, we can look at different ways that we can do more complex tooling. So this is an example where we use the same material, Ultem 1010. We're actually using that to create bladders. So this is from Santa Cruz Bicycles in the US. The challenge was that one of their pro riders wanted a very specialized bike. He wanted something exactly the shape for him. So to do that with traditional tooling meant a huge cost and a long lead time. So they were able to take advantage of 3D printing not only to prototype the frame and get the right shape for that, but to actually produce the tools to do that. So the tannish pieces are actually silicone bladders, putting them inside of the mold. They wrap this in carbon fiber, and this makes it so that for a very low cost and fast turnaround time, they can make a completely custom bike for their rider. So if we had a few hours, we could watch some great videos of him riding, but if you're interested, search for Santa Cruz and Stratasys, and there's a bit more on this. So this is one way that we can use our normal materials to make silicone bladders. But if you need to make 1 or 2 parts, there's another way that works very well for this. So we can also print in a material that dissolves away in water. So typically when we do 3D printing, as we build layer by layer, you always have to be on top of something. So if you imagine you have a hot glue gun, it's okay when you're building or putting glue on top of glue. Then when you drive off the table, this hot piece of glue comes and sticks on your hands and it burns you every time, at least me. So what we do with 3D printing is as we build these layers, we build another material underneath. So this is a supporting material. Normally, we wash this material away in water, and this goes down the drain, and we're left with the part we want. But in this case, we're actually building the part out of the material that dissolves. This means that we can wrap this material in carbon fiber, that we can actually do the layup process like they're showing, so we can print a bladder directly. The disadvantage of this is that since it dissolves, you get to use it one time. So that's why people like Santa Cruz are looking at how do we use FDM or 3D printing to actually make rubber bladders. So this is a good example from Champion Motorsports in the US. So they do custom components for Porsches. So if you need a custom turbo inlet for your car, you can go online, order the parts, and they'll actually 3D print them on demand. So when someone clicks order, this goes onto the machine, they lay up the part, and finally you have your custom 3D printed tool to make your composite part for your car. So one challenge of this and the composites industry as a whole, from what I know about it, I think a lot of you guys are much bigger experts in composites than I am. One challenge that I hear from a lot of customers is that it's the touch time around this that costs them money. So in the aerospace industry in particular, we have a big problem with drill guides. So we've worked with a lot of aerospace companies around the world on how do they do this process better. So the traditional drill guides are large, typically made of steel and machined. This means they're heavy, you can damage parts with them. So what a lot of companies are starting to do is actually just 3D print these. So they can use a lightweight material, they can print it in any shape they need. So this material, if they drop it on the airplane, doesn't damage anything. One operator can easily lift it, move it around the facility, and they can still use it to accurately drill the holes in their parts. So this is from United Launch Alliance in the US. So they build a lot of the space, or a lot of the rockets, or whatever you want to call them, that actually send satellites into space. So they're using this not only for drill guides, but for a number of different things throughout their company, from composite tooling to parts on the crafts to all kinds of stuff there. So if we move even further away from the human touch, then we get into robotics. So the reason that I believe this is an interesting technology for robotics is that we can create parts, whatever shape they need. So here we see some sensors being held at kind of a strange angle. This is from Eckhart in the US. They provide tooling for a lot of automotive companies. But what they're using this for is to position sensors. They can also make sure that the parts that are on the robot, the end effectors, are very lightweight, and there's only material where they need it. So that means that the robot can move just a little bit faster. So for someone doing serial production, if you can go from 21 seconds to 20 seconds, over 100,000 parts, it starts to pay off in a huge way. So not only can we reduce the cost on these parts, we can actually help the robotics move faster than they ever could before. So if we look at another area where we're moving into higher and higher performance, that was a small robot we showed. This is a bit larger part, and a bit higher performing part. So this is from our friends over at Siemens. So what they're doing is they're printing these little black connectors. They assemble them with aluminum extrusion, and they actually pull the entire set of wheels out from underneath the trains when they need to do maintenance. So I always get this word wrong. It's boogie connectors. I don't know why I always get it wrong, but so what they're doing is they're printing these connectors. So if they have a train from this year, it's likely a little bit different design of the boogies than the train from 5 years ago, or than the train from 20 years ago. So they can custom make these to fit whatever angle they need, whatever shape they need. They print these overnight, and they can actually have a custom tool to help them do manufacturing on their lines. So a cool thing about Siemens is that they're not only doing tooling for this. They're also, if you look around, they're doing a lot of replacement parts for their trains. So we have materials outside of the composites realm that actually have certifications to go into rail. So we have the EN 45545 certification. Anybody from rail? Oh, never mind. So we have this certification. We play in this area because when you have these old trains come in, the traditional tool doesn't exist anymore. So people like Siemens or any of the other rail maintenance facilities can look at the parts they have, redesign, and make a replacement part very quickly using 3D printing. So for them, it's a good way to build tools and even to build parts into production and to repair their trains. So when we look at the other possibilities of 3D printing, not only does it make things faster, it helps people make things that they couldn't make before. So this is an example from Eckhart. When vehicles are assembled, typically each lug nut is put on and started by hand, which means that operators are getting injuries. It's when you do the same action every day for a year, this gets to be pretty old. So they designed this tool so they can insert the lug nuts into this. Depending on the car, it's a different design. Plug it onto the wheel, spin it, and it starts all the lug nuts for this guy. So for me, what this shows is not that we all need to build cars. The interesting thing that it shows is that if you have a problem you haven't been able to solve for a long time because there wasn't a technology, 3D printing might be the right solution for you. So we see this in many, many industries, many examples. We have a team of engineers here at Stratasys, and our job is to help customers solve problems. The problem with that is that after we solve the problems, we're normally not allowed to tell you guys what we did. So this is one example we can share, but this is one of many, many examples of where 3D printing is changing people's businesses. So it saves operators time, it saves the company time, and it helps people be more effective. So another example we can look at, this is back to Team Penske. This is on one of their NASCARs. So they're printing the mirror, or the housing for the mirror, and they're actually assembling it and putting it directly on the vehicle. Again, from the show of hands of how many people are in the racing industry, which was pretty close to zero. Oh, we got one now. One. So for you, I'll stand over here so you can see. So for the people in the racing industry, you need one part. But it's lots of different industries that could be the model that would make sense for you. So as people even in automotive are looking at how do we customize vehicles for specific groups of people or specific people, depending on the car, 3D printing becomes very, very important. So we have a lot of research happening in the area of automotive of how do we actually create materials that will work for you guys. We do this in automotive, rail, aerospace, as well as a lot of the consumer goods areas. So if you guys are looking at 3D printing parts and putting them directly into production to sell to a customer, to use on a robot, or to put into tooling, there's a good chance that we have a solution for you. So instead of talking about 6 hours about all the materials we have, we actually do have a booth here at the show over in the other hall. So if you guys want more in-depth information, you can come and talk to us and we'll be happy to walk you through it. We've got 4 or 5 engineers here with us all week to help you with whatever problems. So the interesting thing on this one, you can make custom parts for single people or for small batch production. You don't have to pay for tooling or anything else. A nice story with this is that they put this on the car and they ran it at some of the NASCAR events. And then the NASCAR group changed the rules so they can't use this anymore. Because apparently it was too effective. By controlling aerodynamics around the mirrors, they were able to change things that other people couldn't, and they saw it as an unfair advantage. Which I believe is a pretty good advertisement for our technology. If it gives people unfair advantages, we should all look into that a bit more for our businesses. So to wrap up here, we looked at 4 different areas a little bit. So composite layup tooling, the important piece here is that we can go up to 180C. So if you have tools that you need 1 to 100 plus parts, this is a good solution to get them very quickly for a low cost and lightweight. Custom cores. If you're doing things that require complex tubing made from composites, we can do a few different things to help you actually make the core to go inside of that. Whether we're doing silicone bladders or if we're actually directly printing cores that dissolve, there's an option that could work well for you. Lightweight drill guides, so your operators don't have to carry around these chunks of steel. So in the aerospace industry, we've seen a lot of OEMs and even tier 1s using this and making a huge difference in their manufacturing operations. And finally, production parts. So with the automotive stuff, like I said, it's not only racing that's taking this advantage. If we look at automotive, this is not a dream that I have of someday someone in automotive will make a custom car. We have at least 4 automotive OEMs in Europe producing parts from our technology today. This means that when you order a vehicle, if you take a custom setting for it, or I want a custom cup holder or whatever, and you're one of 1,000 people that did that, they will 3D print your part and put it directly in the car. For them, they save money on tooling, and they get to offer all of us more options. So if you're looking at tooling, we can do it really quickly, lightweight. We can do custom cores without having to have tooling or waiting for the lead time. Lightweight drill guides. And finally, if you're trying to put parts on custom vehicles, on custom products, or just on stuff inside of your factory, we have a good option for that. So if you have more questions, we're in the other hall over here. I'm happy to take whatever questions now, but if you want a bigger conversation and a deeper conversation, we're in the next hall here, and you can feel free to come on over. We're there all week to talk to you guys and help you with whatever we can. So, any questions? Yeah. So we have a microphone coming around so I can hear you too.
So you've mentioned your polymer work, and I think the last time I checked, you had a polymer that was reinforced with fibers. Do you have any plans to move into the metal space?
So, all right, Stratasys people, just plug your ears. No. So we actually at Formnext, which is a large 3D printing convention, we announced that we were looking at this metal space where it's not polymers reinforced with metals, it's actually just printing with metals. So there's an option that we're investigating with building aluminum parts, or aluminium, depending on where you're from, and actually doing that with 3D printing.
Would that be as a service, or?
It's not a product yet. So this is a future investigation, and we still have to define where it goes and what it does.
Thank you.
Yep. Any other questions?
Is that black material is a kind of short fiber reinforced plastic?
Yep. So this material is not. So the material we saw in the Siemens example, sorry, I forgot to mention that, is actually nylon 12 with carbon fiber. So it has short fiber reinforcement inside the material.
If so, are there any flowability problem? How could you solve that problem?
So we have, back in the US, we make 3D printers, but we have a huge amount of development that goes into material sciences. So this goes into the flowability problems and how do we actually make this material flow how we want it to. So we make the materials ourselves and we make the machines. So we're able to build those together to make a solution that gets around all the flowability problems because there's definitely challenges.
Okay. Thank you.
Yep.
So thanks a lot for the presentation. Do you have any experience with the binary jet technology?
A little bit. So we don't, Stratasys as a company does not have binder jet technology.
Okay, what do you think about the future regarding this technology?
I think the future is with polyjet. Oh, no. So polyjet's a technology that we make. If I look at the additive manufacturing world as a whole, there's a lot of different technologies. And if you look at manufacturing in general, there's a lot of different technologies. So if we look at CNC milling, it is not the same as plasma cutting. Plasma cutting's better at some things than CNC will ever be. So I believe that's the same when we look at 3D printing, is that if you look at certain technologies like binder jet or FDM that we showed today, or polyjet, or SLA, or DMLS, or everything has a home. So it's just, you need to understand the advantages of each one and then look at your application and see if that's the right way to go.
Thank you.
You are making composite molds. How about surface roughness and surface tolerance of these molds with 3D printing?
Right. So the surface roughness that we see off the printed molds is typically around 100 microns. So all of these tools that we use are hand finished. So we have an example over at our booth that was actually machined, but they do need post-secondary processes. So we typically use an epoxy, then we'll actually polish that down to whatever surface you need. So we're lucky enough to have a very, very good finishing team. And by team, I mean one person. And so we get very good quality on our molds. But if I finish the tool, it's not going to be very good. So it depends on the skill level of your operator or if you're machining.
Okay, thank you.
Yep. One more, here in the front.
Have you done anything around simulation of the characteristics of the material at temperature?
Why, yes, we have. And conveniently, our partner is right here. So Hexagon has a company called Extreme Engineering. So we're looking at, they do process simulation for us, where we can look at if we build material, because we get to pick where the material goes inside and what order it's laid down. So they take our build files, and they can put it into their process software, and they can tell us what's going to happen. Where do the stresses go? What happens if you heat it or cool it? And they can start to look at all the mechanical properties afterwards of that. So we don't do simulation. Instead, we partner with people that are much better at simulation, and we work together with them to give you guys a more full model. Any more questions? All right. Well, thank you guys for coming. If you do want to have a conversation about this, we'd be happy to show you some sample parts we have. We have tooling. I believe we have some sacrificial core parts. We have some composite parts made off of those. We have people actually from the composites industry here to talk to you. So if you guys are interested in more information, please stop by our booth. It's a long ways from here, but I'm sure you'll make it sometime in the next 3 days. So thank you.